I'd like to begin with this title. Oxidative stress refers to a condition in which reactive oxygen species oxidize cellular membranes and proteins. It is known to be contributing to a lot of disease. Therefore, antioxidants attracted attention because their scavenging activity for loss. Loss are divided into radical and non-radical species in vivo. Specifically, radical loss include superoxide anion and hydroxyl radical. Otherwise, non-radical loss includes singlet oxygen. Since these loss have different properties, antioxidants need the scavenging activity against both types. So we aim to clarify the loss type specific reactivity of antioxidants and explore those with the potential to scavenging a wide range of loss in vivo. We use 5 different antioxidants. They can be classified into 2 groups. First group is carotenoid. We use hydrophobic carotenoids, including astaxanthin and beta-carotene. Otherwise, Crocin used as hydrophilic carotenoid. Second group is vitamin E. We also use hydrophobic alpha-tocophenol and hydrophilic tolurox. First is organic radicals quenching assay using electron spin resonance. Since superoxide anion and hydroxyl radicals are difficult to detect, organic radicals are widely used. ESR measures the types and concentration of radicals in the sample. It is known that the intensity reflects the amount of radicals. Second is singlet oxygen absorption capacity. The absorption spectra shown below each chemical structure. End peroxide generates singlet oxygen at 35 degrees. And generated singlet oxygen is subject to the competitive reaction between the probe compound DPBF and antioxidants. By observing the decomposition rate of DPBF, we evaluate the singlet oxygen scavenging activity. Here is the result of the radical scavenging activity. In this study, we use DPPH radical and galvanoxyl radical. Galvanoxyl radical is more hydrophobic than DPPH. Alpha-tocopherol. This is alpha-tocopherol result. The graph shows the relationship between intensity and the concentration of alpha-tocopherol. As the concentration of alpha-tocopherol increased, the intensity decreased. To evaluate the scavenging activity, we calculate the EC50 value. EC50 represents the concentration of antioxidant required to reduce the initial radical amount by half. These are the EC15. Please take a look at the graph, which shows the logarithm plot of the inverse EC50. Vitamin E shows high scavenging activity. However, hydrophobic carotenoids such as astaxanthin and beta-carotene show no activity. Interestingly, Crocin was the only carotenoid that showed radical scavenging activity. From a structural point of view, this difference in radical scavenging activity are mainly attributed to the phenolic hydroxyl group. But for singlet oxygen, in graph A, the time-dependent change in the absorption spectrum contains only end peroxide and DPBF. In contrast, graph B shows the spectrum when beta-carotene is added. In both cases, DPBF was decomposed by singlet oxygen. However, since the absorption band of beta-carotene and DPBF is overlapped, it is not possible to track the amount of DPBF decomposition. In this study, we applied singular value decomposition to track the change of DPBF. In this graph, the vertical axis represents the amount of DPBF decomposition, and the horizontal axis shows time. The decomposed amount of DPBF was reduced depending on the beta-carotene. So the reaction rate constant K for the reaction between DPBF and singlet oxygen was determined using a fitting equation. Since we have to calculate K, we use the analysis equation to determine the reaction rate constant, Kq, between singlet oxygen and the antioxidant. The slope of this plot reflects the singlet oxygen quenching activity, so we also calculate the Kq values for the other antioxidant using this equation. This as a Kq value, please take a look at the graph, which shows the logarithm plot of the Kq values. For singlet oxygen, vitamin E show very low activity. In contrast, astaxanthin and beta-carotene show strong scavenging activity, and Crocin showed moderate activity. From a structure point of view, this difference in singlet oxygen are mainly attributed to the Porian chain. In conclusion, the antioxidant used in this study can be broadly classified into three groups. The first group is the radical quencher type, and its activity is associated with the phenolic hydroxyl groups. This includes vitamin E. The second group is the singlet quencher type, and its activity is associated with the Porian chain. This group includes hydrophobic carotenoids. The third group is Crocin. Crocin shows high activity against both radical and singlet oxygen. This is because Crocin's unique structure consists of sugar and Porian chain. Our findings suggest that Crocin can scavenge broadly loss in biological systems. In this graph, the vertical axis represents the logarithm of the Kq value. For singlet oxygen, vitamin E, like Tololox and alpha-tocopherol, showed very little activity. In contrast, astaxanthin and beta-carotene show strong scavenging activity, and Crocin showed moderate activity. Just like with radical scavenging activity, this result suggests that the singlet oxygen scavenging activity depends on the type of antioxidant too.